go from the current slide. All right, before we get going on the actual linear algebra, let's review a couple of things. Okay? First, research papers. I've gotten only one in from this class, 1 out of 7. Guess what? You have 1 weekend left, okay, this weekend, because it's due any day next week, but the following week is when finals start. I will accept it during finals week, but you'll lose points, okay, because I don't want to be grading a bunch of research papers at the same time I'm trying to get finals graded and grades average and stuff like that. So you lose points if you wait until you turn it in finals week. It was said at the beginning of the term, last day of class is the last day that you get full credit. And I believe the bonus points have disappeared too, because this week is the last week of, is that right? No. Okay, wait. I'm getting so confused. If you get it to me today, you still can get that one last bonus point. But next week is just your grade, okay? No bonus points. And then the week after that, finals week, done. You're losing points. So please get those to me. Now, have I returned to all of you your first test? They've all been turned in. I've graded them all, and I finally got the last one in, so I was returning them, but I wasn't sure if all of you were here. Second test, I have 4 of the 7 in. One of the second test people is one that's trying to do it remotely, so he hasn't gotten it to me, but the other 2, here's one coming in right now. Okay, incoming, got it. Okay. All right, and then, so try to get those to me as soon as you can too. And you already have your third test, right? I gave it to you already? Anyone who doesn't? Okay. We haven't quite finished chapter 3, but I gave it to you early just because so you could start working on it. Okay. Here and here. Okay. And I hope the other guy got his. I may not have sent it there. I got to get him his. Yuck. Okay. And let me tell you this, not that y'all care, but it's my little sob story. We have what they call a planning hearing coming up next Tuesday. I can't go to it because I'm in class, okay? So, but I've got to get ready for it because I'm department chair. And we have started the process, certainly, but compiling everything, getting it all together, ate up at least half of my office hours yesterday, and the part that I would have been doing other things, I was advising students. So we had orientation this week for this campus, and so there were students all over the place trying to get registered for fall, which is good, but there went my office hours. So basically, papers are stacking up on me right now because I've got to get the planning hearing materials ready and compiled so the other instructors can present those next Tuesday. So that's my sad story. So after Tuesday, I will be grading like crazy trying to get caught up. So anyway, we'll go from there. And see, I only have Mondays and Wednesdays of office hours, so I'll probably be doing a lot of grading this weekend too, if I can find time. We already have 2 things going on this weekend, 3 probably, that it's going to be tough, but I'm going to try to get done what I can. All right, so try to get to me your research paper next week, today if possible, but next week for sure. Your test 2s, those who haven't turned those in, and be working on test 3. Sorry, it's sort of cramming up at the end, but it is. All right, any questions before we get going? So we're on chapter 3, determinants, 3.4 applications of the determinants, and what we had gotten to the point of almost to the point of Cramer's rule. We've been talking about it, but we haven't actually stated it yet. So we're going to state it today just a little bit just to show the generalization to bigger than 2x2s. 2x2s are easy. You probably don't even need Cramer's rule to do them, but it works pretty easily. But let's think about a 3x3. Oh, this takes a while to write. Sorry about this. Ooh, let me get my pen back. Okay. A11x1 plus A12x2 plus A13x3 is equal to B1. A21x1 plus A22x2 plus A23x3 is equal to B2. A31x1 plus A32x2 plus A33x3 is equal to B3. All right, and here's Audrey. All right, just missing 2. One usually can't come, and the other one, hopefully he'll be in too. Let me just repeat what I did. Sorry for the rest of you. Research papers are due in next week to keep from losing points. If you turn them in during finals week, you're losing points. If you get them in next week, you just get your score. Today's the last day to get the bonus point. That last little bonus point that was sitting out there, today's the last day to get that. Okay? And test 1, I've returned to everybody. Did you get yours back? Okay, let me get your test 1. I got the last one in a short while ago. Yep. Oh wait, Lauren, you don't have yours either. All right, here it is. She gets that last bonus point. Okay. And actually, there she should. All right. All right. So get your research papers in and get your test 2s in. I've gotten 1 or 2 today, so those are coming in nicely now. Test 3, did you get it? Okay. We're finishing chapter 3 today, but I gave it to the others early yesterday, or Tuesday, just so they could be working on it if they want to. Too far. Okay, getting closer. Gotta remember to send Julian his. Okay, so this is what we're doing. There's a system of equations, and they sort of, I guess, randomly chose to show how you can use Cramer's rule to solve for any one of the variables. You pick a variable, x1, x2, x3, I don't care. Pick one. Say again? X1, okay. So what would be X1? Cramer's rule would say, what is the, using Cramer's rule, what would be your X1? I'll do the denominator. It's the determinant of your coefficient matrix. A11, A12, A13, A21, A22, and A23, A31, A32, A33. Always, for every variable, x1, x2, x3, that is your denominator. If you had a 7 by 7 matrix, it would be that 7 by 7 coefficient matrix. That would be your denominator, the determinant of that. Okay? Now you tell me what would be the determinant. Oh, what would be your numerator of that x1? Second? Okay, yes. Instead of your coefficients that would be for x1, you put your b's. B1, B2, and B3, and then the rest stay the same. A12, A13, A22, A23, A32, and A33. That determinant is your numerator. That's your answer. So basically, you can write down your answers. Of course, there's a bit of work to do to get to them. A 3 by 3, I think James likes the expansion method, and that works really nicely. So it's not too hard to do it with Cramer's rule. Is it any easier than row reduction? Don't know. The good news is most of the time your coefficients are integers, right? Whereas it doesn't take long in, say, a 3 by 3 or bigger matrix to run into fractions really, really easily, okay? And the odds are you're going to wind up with fractions with this because guess what? You got a denominator. And if that denominator is anything other than 1, okay, you're going to have some type of fraction. Now, of course, if the numerator is a multiple of the denominator, then you'll lose the fraction. But generally, you're going to wind up with fractions. But the good news about determinants, you usually don't get them until the very last step, when you write down the determinant of the numerator of the determinant of the denominator. So if you don't like messing with fractions, which you quite often run into with row reduction, determinants avoids those. Okay? And they're not that hard to do, especially a 3 by 3. 4 by 4s get a bit more involved, but if you can remember, if you can do row reduction using the technique of multiplying a multiple of one row or column by another, you can still do your determinants fairly easily. So we'll get off that for now. So let's give the theorem for Cramer's rule. If a system of n linear equations and n variables n equations and variables has a coefficient matrix I think they call it A. Goodness gracious. A. With non-zero determinant okay. Why is that necessary? Why does the determinant can't be 0? Second?
Because then you have 0.
Yeah, if you had the coefficient, you'd have 0 in the denominator, and that means no solution. Well, don't quite take that at its word. That means you can't get the determinant using Cramer's rule. I mean, you can't get the solution using Cramer's rule because that 0 denominator, 0 determinant says it's a singular matrix, a non-invertible matrix. You know, they have all these words for it. We can't use the matrix technique or the determinant technique for it. You can use row reduction, and you're going to wind up with a row of 0 somewhere. Okay? If you do row reduction, which means you're going to have a parametric form. So that's a little bit different from it doesn't exist. So don't say it doesn't exist. It's just that you can't use Cramer's rule if it's a non-invertible matrix, A. Okay? So then the solution of the system and you can just, I mean, it looks really easy. X1 is equal to, now, by the way, they call this form up here A1 because you substituted the constants for your X1 variables. So that's the the determinant of A1 over the determinant of A, okay? So we're going to use that nomenclature here. This will be the determinant of your coefficient matrix with the constants put in place of your x1 coefficients over your A. x2 will then simply be the determinant of your A2 matrix, which is put your constants in place of the coefficients of x2 over the determinant of A. x3 would be your determinant of A3, which is the constants put in place of your coefficients of x3 over the determinant of A. Dot, 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 until you get up to x sub n, because you have n variables, is equal to A sub n. That's the coefficient matrix with the constant substituted for the column that had the coefficients for x sub n over absolute, the determinant of A. Okay. Where the ith column of A sub, I can't read that, I think it's I, is the column of constants with the system, in the system of equations. That's what I've been saying all along. All right, so let's do Kramer's rule on a 3x3. Here's our equation. Minus x plus 2y minus 3z is equal to 1. 2x plus z is equal to 0. 3x minus 4y minus plus 4z is equal to 2. All right. Let's solve this for x, y, and z. How would you begin? Second? I can't hear.
With a coefficient matrix.
Okay, let's start with the coefficient matrix. I like. What are you going to do with it? Hint. What is the coefficient matrix? You tell me that first. Negative 1, 2, negative 3. Second?
You want the...
No, we're going to do Kramer's rule.
Okay.
Yeah.
2,
0,
0,
1, 3, negative 4, 4. Okay. Now what are you going to do with that? Yeah. Second? Take a determinant. That's what we're doing. And James walked out, so I want to ask you, how do you want to do a determinant of that one? There's at least two relatively easy ways to do it. Second row and go along it. I like that one. So James isn't here, so we'll do it. Okay. So what does that mean? What are you going to do? Second, wipe out the second row, but before we do it, I want to write something down. Okay, but I first determine what's the sign of its position. What is it? Negative, so that makes it a negative 2. And then I wipe out the second row and the first column, because that's where that 2 came from. And then I do the determinant of what's left. Can we do it right there? I think we can. 8. Negative 4. That's negative 2 times a negative 4. Okay? Now, enough of that. Let me erase these construction lines here, because, and Patricia was very wise in her choice of the second row because it has a 0 in it. Second column would have done as well, but it has bigger numbers, so I like the second row. Okay? So we move on. The 0 means we don't have to do a thing for that one. So move on to the 1. And what question do you ask yourself first? What is the sign of that position? And that the answer to that is negative. So that's going to be a -1. And then let's wipe out that column. And can we do this determinant?
4 and 6, it's -2.
Second?
If 4 and 6, it's -2.
-2 times a -2. So the determinant of that would be 8 plus 2 equal 10. Okay, what does that tell you? One thing. It will have an exact, distinct solution. One and only one solution. What would have been required for it not to be true? Determinant equals 0. Then you wouldn't have either there's no solution or infinite number of solutions. And Kramer's rule doesn't tell you which one. Okay, that's sort of a disadvantage of it. All right, so that, and what does this also give you? What is that 10 going to be now for you? Your denominator of every one of your x, y's, and z's. Okay? So, how do we get the numerators? Which one you want to do first? You pick. I don't care. Which one you want to do? X. So I'm going to call that a sub x. And it's going to be the determinant of a sub x. And what do you think I mean by that? What will I put in here?
For the first column, you have like the 1, 0, and 2.
Exactly. 1, 0, 2 becomes your first column because the coefficients for x are being replaced by the constant. And the rest of it stays the same, so that'll be a 2, 0, minus 4, and a minus 3, 1, 4. Okay, I hope I copied them right. All right, that's going to be even easier. Okay, how do we do this one? What is that determinant?
You use the second row.
A second row for sure on this one. And what's the first thing you determine there?
It's a negative position.
Second?
The position is negative.
Yeah, the position's negative, so that's going to be a -1. And we'll wipe out that row and column and row or whatever, okay? And what do we have left?
0.
Second?
Negative 4.
-4.
So -8.
Second?
-8.
-8. Okay? So that's going to be 8. All right. We can right now write down what x is. X is equal to 8 over 10, which is 4 over 5. Done. We already know what the x is. Okay? You don't have to do it now, but you could. All right. What's the next thing you want to do? It's up to you. Do something. Second?
Solve for y.
Okay. Do your a sub y. Okay. All right. This will change. And this will change. That one will stay the same. Okay. So let's do a, oh, let me, while I'm here, let's get rid of this one. Okay. All right. Now we're going to do a sub y. And what will that be? I lost 2 rows before. Fill me in what goes in those 2 rows. Help me, help me.
-1.
-1 for sure.
1.
1. 2, 0, 3, 2. Got it. Okay? So, how do you want to do this one? Second row. Okay. You left the room so they preempted and not doing the expansion. They're just choosing a row or column and choosing the second column. So how do we begin that? Sign of the 2 there is what? Negative 2. And we'll wipe out that row and that column. And what do we have left?
-2.
Second?
-2.
Okay, I got the -2.
4 minus.
4.
Minus 6.
Okay, minus a -6, isn't it?
4 plus 6.
Yes, 4 plus 6. Okay. And now we'll get rid of those construction lines. Okay. And we get to skip the 0 because it doesn't contribute anything. I hope not be, yeah. And then we go to what's next?
The sign.
The sign of that position is, and the number is 1. And now we'll wipe out that column. And what is our determinant that's left?
-2. -5.
-5. And what does this produce? -25. Wait. Nope. This is a -20, right? And this is a +5, so that gives you a -15. Can you write down your y now? It's your a sub y minus 15 over your determinant of a, 10, which is simplify. Second?
3/2.
-3/2. Perfect. Okay? Now, I'm sort of glad I'm doing these because I'm using the same space for the other. One more component to figure out, variable to figure out, and that's the y. And how do we do that? We put the a sub z in place. So that's going to wipe out that one and wipe out this one. And we'll wipe out, actually that's going to stay the same. Oh, I'm going to leave that alone. Okay. Tell me what your a sub z is going to be. First column's the same. What's the rest of them? Anybody? Help me? Someone say something? A sub z.
That second column stays the same.
Second column stays the same, so that'll be a 2, 0, -4. Third column becomes
1, 0,
1, 0, 2. Now, any suggestions here? Let's use that second row for sure. Okay? We're going to use the second row, and we already know what the position is. -2 goes in there. So we'll wipe out that column and row, and what do we have left?
4, -4 to
Second?
4 to 8.
8. 4 plus 4 is 8. Okay? So So that's going to be 8 times negative 2. Negative 16? Ugh. So that means our z, strangely enough, is going to be negative 8/5. I guess that's okay. What, they didn't do the whole problem? Yep, well, they did on the side. Okay. Negative 4/5 for x, negative 3/2 for, oh, wait. 4/5 for x, negative 3/2 for y, and negative 8/5 for z. Yes, we did. Now, of course, if you wanted to check them, just plug in these values and see if that's what you get. That's sort of the harder part, but it's not impossible. It's not bad. It'd be negative 4/5 plus minus 3 plus 24/5. So that would be 25/5. Yeah, that's not hard, but 25/5 is 4 minus 3 is 1. Yeah. So it's not impossible. Okay. The next one, 8/5 minus 8/5 is 0. That was really easy. I'll leave the rest to the student. You know, that's what they always say when you don't want to do any more. Okay. Is leave that to the student. But you can check those and see if that's what you get. Now, that's a straightforward, sort of broad application. Now, for most intents and purposes, this is going to be longer to do than row reduction. Okay? Because row reduction, you just do one row reduction, you know, with augmented matrix, and when you get it down to an identity matrix here, you have your solution. So you don't have 3 parts and you know, all that to do. Sort of the good news here that doing that the coefficient matrix to begin with, that lets you know whether it's going to be a unique system or not. Okay? If that's non-zero, you will have 3 unique solutions. Okay? You don't see that doing the other that quickly. Okay? If you get a 0, though, that tells you either you have no solutions or infinite number of solutions. Kramer's rule doesn't distinguish between the two. It tells you whether you have one or only one solution or not, and that's all. Whereas row reduction, if you have a row of zeros at the bottom, you have an infinite number of solutions. If you have all zeros except for a non-zero equal to, that means you have no solutions. Okay. Now, once you do that first matrix there, you got your denominator for all 3 of them. Okay? So then you just have to do the other 2 matrices. And 3 by 3s are usually pretty easy to do. Okay? 4 by 4s, 5 by 5s, they get more difficult. But they also do for row reduction, but still it's a pretty standard process, and it gets much easier to do in time. So, now, possibly, if you have a package that does determinants for you, then just feed it in the numbers and it'll pop out the answers to you. Whereas usually you don't have packages that do row reduction. You know, I don't think you do anyway. So there's advantages and disadvantages. Let's go to a whole new application of determinants. Areas, volumes, and equations of lines and planes. What? You can do this with determinants? It says they have many applications, analytic geometry, and one application is finding the area of a triangle in the XY plane. So here's how you do it. If you have these vertices, x1, y1, x2, y2, and x3, y3. Okay? If you have those 3 vertices, now, get a triangle. Of course, any two of these are going to form a straight line, right? You can't have all three of them on the same line. In other words, if you had that, you're not going to have a triangle. Your area, the procedure we're going to do is going to tell you the determinant is 0, okay? Which happens to mean the area is 0 too, because it's one line, not three distinct nonlinear points. So anyway, here's how you find the area. They just tell you, okay? It's equal to, now this seems bizarre to begin with, plus or minus, okay? Wait a minute, can an area be plus or minus? No, an area is going to be positive, but a determinant could be plus or minus, so therefore you need the plus or minus sign to assign to it to make sure your area is positive. So that's where that comes from. Then, strangely enough, you have a 1/2 there, okay? And then you have the determinant of the following matrix. Now, x1, y1, 1. x2, y2, 1. x3, y3, 1. Okay, that's the matrix. Okay, it has to be square, so you can't just put the ordered pairs down there. That would be rectangular. The third column is always ones. 1, 1, 1. Okay. The others are your xy coordinates. Okay? So it's that determinant. Now, there's no guarantee that this determinant is going to be positive. Okay, if the determinant is 0, hang it up, these are collinear points. Okay? If the determinant is not 0, these are non-collinear points, so you're going to have a triangle, but this could be positive or negative. That's why you have the plus or minus here. If this thing's positive, use plus. If this thing's negative, use minus to make it positive. Okay? Because the area is always positive. And the 1/2 is just there. Not much you can do with it. All right. Okay. Now, they give a proof here, and it's a really neat little proof. And it also tells you where the 1/2 comes from. But I really don't think we have time to do it. So I would suggest that you read through that. I wish they had the PowerPoint and had a figure here and we would talk about it. But the reason I said that's where the 1/2 comes from, what you're measuring is the area of the trapezoid. Okay? Each one of these lines now, for right now we're putting them all in the first quadrant. Okay? All those x's and y's are positive, or at least non-negative. Okay? So you form a line here, a line here, a line there, something like that as your triangle. And every one of those, if you drew down to the horizontal axis, forms a trapezoid. Because two parallel sides and then a slant side somewhere. All those sides assume they're slanted, one way or another. Well, then every one of those represents a trapezoid. What's the area of a trapezoid? 1/2 the common dimension times the sum of the other two dimensions. Because you take that trapezoid, flip it over, and you get a rectangle. So that has twice, it's twice the area that you need, so that's where the 1/2 comes from. All right. We'll leave that alone. Let's just do an example. Find the area of the triangle whose vertices are 1, 0, 2, 2, 4, 3. Okay? I'm pretty sure this is not going to be collinear. 1, 0, we go over 0 here, don't go up or down any. Go 1 to the right, don't go up or down. The next one is 2, 2, somewhere up here, and the next one's 4, 3, somewhere here. So you have one here, there, yeah, non-collinear. Okay? So you find the area. Tell me how to do it. Area is equal to, what's the formula? Plus or minus 1/2 times this, what determinant?
First row is 101.
101. 221. 431. You got it. Okay? That determinant. All right. Since James is back, I think I know the answer to this question. How do you want to solve it? Huh? Expand. Okay, let's try expansion. You could do row reduct, or do that first row. That would work okay too. But expansion's not bad either. So let me get my pen back. And what would go here? 1 0 2 2 4 3. Okay. And now we do our down diagonals. This is going to be plus or minus 1/2 of, what's that first down diagonal? 2. 6. Okay. Up diagonals. Minus 8. Minus 3. 0. Okay. So this will be plus or minus 1/2. What goes in there? Well, 8 minus 8 is 0. Minus 3. So we're going to use your minus here, and that would be 3/2. That's the area of that triangle. Okay? And that would be square units, whatever those are. Okay. Now, if you happen to have 3 collinear points, and surprisingly, you would get that in this case by, let me wipe out this. Okay. All right. Okay. The surprising thing is, on this one, I didn't make it surprising enough. Make that a 0 1 rather than 1 0. And let's see what happens now. So this will make this a 0 and that a 1. Okay? All right. Plus or minus 1/2. And now let's do the down diagonal. 0. 4. Plus 6. Up diagonals. Minus 8. 0. Minus 2. What do we get? 0. Now, this is literally, in this case, your area is 0 because all these 3 points are on the same line. If you look at the figure in your book, if you've got a book, you'll see those 3 points all line up. 0, 1, and I guess I should change it up here. And here's how you can tell. The difference here is 2 and 1. The difference here is same slope. 1 over 2 is 1/2 slope. Okay? So 1/2 slope, that point's on both lines. Okay. That's all on the same line. And sure enough, if that were a triangle, its area would be 0 because it has no area. It's a line. Okay. Now, that also gives you something else. We just did it whether we thought about it or not. I think I'll clear my screen so I can write but more neatly. Maybe not neatly, but whatever. If you have 3 points, okay, x1, y1, x2, y2, and x3, y3, okay? If when you do the determinant of x1, x2, 1, x1, y1, 1, x2, y2, 1, and x3, y3, 1, yuck. Okay, let me start over. Okay, if you do that determinant, and that determinant is 0, then what can you know about those 3 points? Collinear, exactly. So the test, if 3 points are collinear, if and only if that determinant is, okay? So, there we have that. Now, we'll extend that one more time, okay? If you only have 2 points, okay? If you only have 2 points, x1, y1, and x2, y2, then what you do is, to get an equation for the line that those 2 points form, is this. Your top line, just lose the subscripts. X, y, 1. X1, y1, 1. X2, y2, 1. Okay? Now, if everything else was a same, you just moved everything down, but those are, now, if you do the determinant of that, this is a little messier, but it is doable, and I would suggest doing it by expansion. I think is going to be the easier way to go, and James likes it, so we'll go with that. Okay, x, y, x1, y1, and x1, 2, y2. Okay, well, don't need that last bar, this isn't a determinant, but if you go like this, you have x, y1, actually I want to write that as y1x, I think. Because x is a variable, y is some number. y1x, whoa! I messed up, sorry. Okay, y1x, because that 1 is your third one, okay? Yeah. A little bit better there. Plus x2y, right? Plus x1y2, right? Minus x2y1 minus y2x minus x1y. Okay? Now, if these two are on the line, which they obviously are, any 2 points are collinear, right? So if these are on the line, and these are your variables, then this thing has to be 0, because the variable is also on the line. Okay, whatever number you put on there. So this thing has got to be 0. Okay, that determinant has got to be 0. Well, let's clean this up a little bit and see what we got. We got y1 minus, there it is, minus y2 times x plus x2. I've done this one and that one. Minus xy. Y. Goodness gracious. That's that one and that one. Is equal to, I'm going to put the other on the other side, x2 y1 minus x1 y2. That's your constant. So this gives you your coefficient of x, that's your coefficient of y, there's your constant. Okay? Now don't try to remember the formula, just do it. It's pretty simple to do. Okay? So find an equation of a line that passes through these 2 points, 2, 4 and negative 1, 3. All right. Number 1, we know how to do it using get the slope here, one of the points, use slope point formula. We know how to do that. And that's not hard, okay? But let's do it this other way, okay? What do we say the technique was? Hint. Hint. Help me. What's the top row?
Are you referring to the slope?
No. Okay. I'm using the technique we just described to get a equation of a line. Those 2 points to get the equation of a line. I said you could calculate the slope and then use one of the points to come up with it. Yeah, we know you can do that. Let's use this determinant technique. What goes in your determinant? Top row was x, y, 1. The variables x and y. Second row was 2, 4, 1. Third row was negative 1, 3, 1. Okay? Now, I don't know if James is speaking up, but if I were to ask him, I think he'd say expand, wouldn't you? Okay? So let's do that. What you write is the next 2 columns. X, Y. 2, 4.
Negative 1, 3.
Okay? Now, excuse me, let's do our down diagonal. What do we get? Oh, and this thing is equal to 0. That's required for it to be an equation of a line because these 2 points are on the same line. Okay, so they're collinear. And the xy values represent other points on that line. So 0 is equal to, first down diagonal, 4x, next down diagonal, minus y, next diagonal, plus 6, next up diagonal, if you said something I couldn't hear.
Positive 16.
Okay, no, 4, okay, 1 times 4 times 1. That's just minus, it's a positive 4, isn't it?
Positive 4.
Yeah, positive 4. Okay. Next up diagonal. Minus 3x, right? Next up diagonal. Minus 2y. And this thing's equal to 0. I've already got the 0 in front, but I'm going to put it at the end because that's where I like to have it. Okay, let's combine like terms. Combine like terms. X minus 3y second plus 10 is equal to 0. Okay? Sorry. Eyes are going crazy on me. And I kind of like that better to say x minus 3y is equal to negative 10. Okay. Now, let's go back and do the old-fashioned way and see. First thing, you need to tell me the slope between those 2 points. Anyone remember what the slope formula is? Anybody?
Slope is the rise over the run, right?
Right?
Y equals mx plus b.
Say it again. You may have said it right, I just can't hear.
Y equals mx plus b.
Okay, we're going to do that, but we need the slope first. What's the slope? Okay, Audrey just took a little break. Do we all want to take one? What you think? Yeah or nay?
Yeah.
Okay, let's do one. We'll pick up on this when we come back. All right, have y'all figured out the slope yet?
It's y2 minus y1.
Y2 minus Y1, which you want to be the Y2, I don't care.
3.
3. So 3 minus 4 is negative 1.
Negative 3.
Over negative 3, which is 1/3. See, it didn't really matter which one you used. You could have done 4 minus 3 is 1, and 2 minus 1 is 3. Either one would have worked. 1/3. That's your slope. Okay? Now, someone mentioned a slope formula, a point slope formula. How was that? Anyone remember?
Point slope is y2 minus
Okay. Y minus Y1
n
equal to m times
x minus
x minus x1. Now you get to choose, I don't care which x1 and y1, just pick one of the points, either one, and plug them into the x1 and y1. Y minus, you choose either point. 4 is equal to 1/3, that's your m, times x minus 2. Okay, if you choose 4, you got to use 2. Okay, so that gives you y minus 4 is equal to 1/3 x minus 2/3. Don't you love your fractions? Let's add 4 to both sides. I can't get the 4 plus sign to show up. How many thirds is 4? 12 plus 12/3, right? So this would then produce y is equal to 1/3 x, and that would be plus 10/3, wouldn't it be? Minus 2/3 plus 12/3. All right. Well, I think the logical thing would be multiply everything by 3. That would give you 3y is equal to x plus 10. And then if you wanted to subtract 3y from both sides and subtract 10 from both sides, you would get x minus 3y is equal to negative 10. Ding, ding, ding. Same thing we got before. So, I don't know. That was pretty easy to do, wasn't it? You didn't have to remember a bunch of formulas. Okay? Just do it. And the math is pretty easy. Okay? And again, you avoided all your fractions, got it into that form without having to go through any fractions whatsoever. All right. See how it works? All right. Now, so we did area of a triangle. We determined whether the lines were collinear or not, and then we came up with the equation of a line. Well, guess what? Let's do some volumes here. The formula for the area of a triangle is in a plane has a straightforward generalization to three-dimensional space, which is presented without proof, thank you very much, as the following. If you have a tetrahedron, that's a four-sided figure, okay? No, it's a four-pointed figure, okay? It is four-sided too, but every side is a triangle. We're not talking about a square, which is actually six sides. Four-sided figure, and each side's a triangle. That's a tetrahedron. So the volume for a tetrahedron with vertices, and this is in three space now, x1, y1, z1, x2, y2, z2, x3, y3, z3, x4, y4, z4. Okay. That volume of that tetrahedron, anyone want to make a guess? V is equal to? It's going to be a plus or minus. This is the part that might be a little strange. 1/6. Not 1/2, but 1/6. Okay? The determinant of, now you should be able to guess the determinant. Think back what it was for your triangle. X1, wait, Y1, Z1, 1. Okay, next. X2, Y2, Z2, 1. I always want to put a 2 there. It's not. It's a 1. Next. X3, Y3, Z3, 1. Got it. All right, I think things just got a lot more complicated, didn't they? Okay, because you got a 4x4 determinant to do, and there's not a simple expansion to do it. You're going to have to do a bit more work on it. Okay? Now, again, there's no guarantee that's going to be positive, so that's why you have the plus minus in front, because all volumes have to be positive. Okay. And the 1/6, not telling you where that came from. Now, they are going to be extraordinarily generous to us. Okay? In that, here's the tetrahedron, the vertices of the tetrahedron they want us to find. 0, 4, 1. 4, 0, 0. 3, 5, 2. 2, 2, 5. Now, I have no way of looking at that and knowing whether that's going, any of those are, 3 of those are collinear. If they are, you're not going to get a volume, okay? But we're going to assume, and they drew the picture, that they're not, okay? So, how are you going to get the volume of that tetrahedron? I'll start out with the plus or minus. I'll start out with the 1/6. You tell me what to put in the determinant. Zero, 4, 1, 1.
4, 0, 3, 5, 2, 1. 2, 2, 5, 1.
Okay. Now, to do a determinant of that one, what would you do? You tell me. Anybody?
Expand.
Second?
Expand.
I can't hear.
Expand.
Expand? You can't do that with 4x4. That's only for a 3x3. Okay? If y'all are sitting there thinking about maybe eliminating something, you could do that, or you could just take it the way it is. If you were thinking about eliminating something, and remember this is a determinant, and you can do this with determinants, you could do this minus 4 times that, and that would give you another 0 here. And that would not be a bad way to go if you wanted to do that. Or you could just expand, do your, pick a row or column and go for it. What you want to do.
We did the second row.
What's that?
What if we
Choose the second row and just go. Okay, let's do that. So, don't forget your plus or minus 1/6. That's going to be out front. Okay? Okay, now, start with that 4, right? What's the first thing you need to determine there?
what its position is?
Yeah, the sign of its position, and what is that?
Negative.
So that's going to be a minus 4. And then that's going to be the determinant of what's left over. Well, that's going to be a 3x3, which we probably will expand. Okay, 4, 1, 1. 5, 2, 1, 2, 5, 1. Okay? And since we're probably going to expand, I'm just going to leave off that last line. Okay? To give us room to expand. Okay? And let's just, so we don't forget to do it, what's going to be the next step after we expand that? Come down to the 1. And you got to make the same determination. What is its sign? Plus, minus, plus, minus, plus, right? So that's going to be a plus 1 times its determinant, which you're going to have to expand. So I'm going to erase that line, okay? And we'll wipe out that row. A column, and then we have 0, 4, 1, 3, 5, 2, 2, 2, 5. Okay, and we'll probably expand that one. So let's expand that first one, which would be a 4, 1, a 5, okay, 5, 2, and a 2, 5. Okay, and expanding this will be a 0, 4, 3, 5, 2, 2. Okay, so plus or minus 1/6 times a minus 4 times, okay, down diagonal, 8 plus 2 plus 25, up diagonals,
Minus 4. Minus
20 you said? Okay,
minus 5.
okay. And then we have a plus 1 times, down that diagonal,
0.
0,
16.
16,
6.
plus 6, up diagonal,
Minus 10.
minus 10,
0.
woo,
Minus 60.
minus 60. Where did that come from? Okay, let's see what we got in here now. All right, here's a plus 25 and a minus 25. Those go out. And you got 10 minus 4 is 6 times negative 4. So you got a plus or minus 1/6 times minus 24, right? Okay. Down here, yep, you got a minus 70 and a plus 22. And I think that's 48 minus 48, is that right? I'm doing it in my head, and my head's not working well today. 22 minus 70. Yeah. No, I'm sorry. That's 70. 48. Is that what I said? I don't remember. Okay, minus 48. And that's going to be a minus 48. Okay, whoa. So that's plus or minus 1/6 of negative 72. 6 will go into 72. 12 times we'll use the minus sign. So it looks like the volume is going to be 12 cubic units. Whew. I looked on the wrong page. I thought, how did they get that? No, I was looking on the wrong page. Yeah, 12 is the answer. Okay? Now, did I need that up? Leave that up a little bit longer? Okay. A little messy, but okay. Now, maybe you want to determine what would have happened if we had just a one column reduction and made that a 0. That would have made our calculations as one expansion. So you might want it to go that way. But I'll let y'all make the choice, whichever. Okay. Let's clear this and see what we got here. If 4 points in a three-dimensional space lie in the same plane, not the same line, but the same plane. Now, of course, if they're in the same line, they're in an infinite number of planes, but they're in the same plane as well. Then the determinant in the formula will be of the tetrahedron will be 0, because you don't have any volume if you're all in the same plane. So here's another test. If your determinant, if you got 4 points, I don't want to write them all again, but you know, x1, y1, z1, x2, y2, z, all those. If they're coplanar, in fact, all in the same plane, then the determinant of x1, y1, z1, 1, x2, y2, z2, 1, x3, y3, z3, 1, and x4, y4, z4, 1, 4, 1, then that determinant has to be 0. It must be 0. Okay? Now, if that's the case, then you can just eliminate the first row's subscripts and move all the others down 1, and then this gives you, I'll just write it again, x, y, z1, x1, y1, z1, 1, x2, y2, z2, 1, and x3, y3, z3, 1. So that means if you're given any 3 points, you can find the plane that contains those 3 points by setting up this determinant and set it equal to 0. That guarantees you you're going to find the equation of that plane. Now, many of you found equations of planes before. If they're in a plane, they're all going to be at first powers, but you'll have all 3 variables involved there. So let's do example 8 with real numbers rather than variables. Okay, so let's find an equation of a plane passing through these points, 0, 1, 0, negative 1, 3, 2, and 2, 0, or negative 2, 0, 1. Okay? Okay. Now, how do you do that? X, Y, Z, 1. Help me. 0, 1, 0, 1. Blast off. Okay. -2, 0, 1, 1. Whoa! Where did that come from? 1. All right. Woo-hoo. All right. How would you proceed? Now, guess what team? I don't think row and okay. Row reduction may help you some. Column reduction, you're going to wind up with pluses and minus z's and x's or y's, you know. So I don't think that'll help you any. If you could do a row reduction with these 3 rows and not mess with the top one, that may be beneficial. Okay. And I really don't see any super easy thing to do here without introducing fractions or other things. So I think it's probably just going to be a good idea to go with second row. Okay? Let's see what it gives us. We want it to be 0, right? And what will that row reduction be? Let's do the second row. So where will we begin? You see that? What's that?
Are you asking about the sign?
Okay, just where to begin. Okay, sign's a good place to begin. What's the sign of that position?
Negative.
Is it? Plus, minus, plus, plus, minus, plus. It's on the diagonal. They're all plus. Right? So that's plus. So it's going to be 1 times the determinant of what's left over, which is, let's wipe out that row and that column, x, z, 1, -1, 2, 1, -2, 1, 1. Next. Help me somebody. Okay. Do a little hint here. Take that out. Where do we go next? Right?
We'll set up a 3x3 using that 1.
Okay. Okay, but first you got to determine the sign of that position. What's that? It's positive also. So plus 1, and we don't even have to write down the ones I just did for effect. And then you wipe out that row, a column, and what do you have now?
X, Y, Z.
X, Y, Z.
-1, 3, 2.
Got it?
-2, 0, 1.
Okay. So now we start our expansion. And, oh, yuck! I meant to leave more room because I wanted to expand this way. Okay, erase that one too. So it's going to be a little cramped, but I think we can do it. All right, x, z, -1, 2, and -2, 1. Okay, I think what I'll do is erase this and just put a plus here. Okay, and same expansion here. That's going to be xy -1, 2, and -2, 1. All right, let's do our expansion. 1's Fine, okay. That would be 2x
-4.
It's this 1. Again, I've got it too cramped. See, this was the first one. Here's the next one. Z times 1 times -2. That's -2z. Okay? And then this one, -1. Okay, now let's do the up diagonals. +4. Up diagonal 2. Minus x. And up diagonal 3. Plus z. Okay. Plus, down diagonal here, 3x. Down diagonal here, minus 4y, right? Okay. Down diagonal there, minus z. Up diagonal here, plus 6z. Up diagonal there, finally, okay. Up diagonal there, plus y. No, you're right, plus y. And this is all equal to 0. I was going to put it at the end, but I don't have room, so I'll put it there. All right, let's combine like terms. Here's a 2x, a minus x, a plus 3x. So that's going to be 2 and 3 is 5, minus 1 is 4x. Okay, let's do our y's now. That looks like only 2, minus 3y. Let's do our z's. Minus 2z plus z minus z. So this plus z minus z are going to go out. So it'd be 2z plus 6z. Minus 2z plus 6z is plus 4z. So those are taken care of. And now our constants. And that's going to be a 3 there, and that's all. Okay? Plus 3 is equal to 0. So this could be written as 4x minus 3y plus 4z is equal to -3, if you prefer writing it that way. And that is an equation of a plane. 4x minus 3y plus 5z is equal to -3. I must have missed one. Okay, that's minus 2z, we got that one right. A plus z, we got that one right. A plus 6z, we got that one right. Oh, and a minus z, we got that one right. So evidently I did something wrong with my matrices. I don't see it. Do you find my mistake somewhere here? They did, by the way, do a reduction or a thing and supposedly made it better, but I have not found where I messed up yet. I don't know. I've got a 4, they got a 5, and I don't know how we could. Doesn't really matter. Okay. Too much, I guess. Okay, according to Kepler's first law of planetary motion, orbits of planets are ellipses with the sun as one focus. The general equation for a conic section, such an ellipse, and they give it here, to determine the equation of orbit of a planet, an astronomer can find the coordinates of the planet along its orbit at 5 different points, use the determinant. Not me, babes. Okay. The thing is, how do you set up a grid in space anyway? I don't quite know that. So it's an application. This finishes 3.4. Homework exercises, any of the odds 1 through 7. Do number 9 if you choose. It's a proof. Do number 11. 13 is a good one. 15 is a proof. You can do it or not, up to you. Any of the odds 17 to 29. Any of the odds 31, either 31 or 33 or both. It's up to you. 35, try to do 35. Then either 37 or 39, either 41 or 43, either 45 or 47, or both. You can do both if you choose. 49 or 51, 53 or 55, 57 or 59, do 61. 63 is an applied problem, and that's it. Okay? And by the way, answers for the odds are in the back, but also worked out solutions are at calcchat.com. So if you can't get the answer in the back, go and see how they work it out at calcchat.com. Now, if you need a few more exercises to review, you can do any of the odds 1 through 17 on review exercises. And again, calcchat.com has worked out solutions to the odd number exercises. You can do either 19 or 21 or both. You can do 23, do 25, do 27, either 29 or 31, 33 or 35, any of the odds 37 to 41, 43, 45 is a proof if you'd like to do it. 47, interesting sort of a little problem there. 49 or 51 deal with something called the Jacobian. And this deals with partial derivatives. We're gonna, if we get far enough, we will be hitting Jacobian later, so you can introduce yourself to it now if you'd like. Okay? There's some writing ones, or 53 and 55 are writing things, only if you choose to do that. And I think, oh no, there's the next page. 57 you can do either 59 or 61 or both. 63 you could do. 65 you could do. 67 you could do. 69 you could do. 70 you could do. True false either 73 or 75, and that looks like it. All right. Now, I've already given everybody your test 3, right? Anyone didn't get test 3? Okay. All right, we're ready then to move on to vector spaces. Now, new kind of concept here. What have we got? 5 minutes? Is that right? A little over 5 minutes. We're not going to get the whole chapter done because this is one long chapter. So let's get as much as we can done, and let's at least talk about what we mean. Maybe number 1 with what in the world is a vector? Anyone have an idea? We've mentioned it a few times before, but we never have really fully dealt with it. What is a vector? Okay? Let's start with something we probably realize, what we call a line segment that goes from here to there, or from here to there, or from here to there. That's a line segment. Okay? Now, a line will go infinitely from here to there, okay? I mean, there is no here or there. It's just all points are along the same slope, you know, they're on the same line, and that could be here, here, here. A vector is kind of in between the two. It has one fixed point, and the other point goes forever. Unless, of course, it's a measure of something, and then it will be more like a line segment. But a vector has two characteristics. It has, I'm sorry, I guess I shouldn't have said the other. I guess the best definition would be a directed line segment. It would be back to our line segment, but now it has two characteristics. The magnitude of that line segment, which is its length, and the direction of that line segment, which you usually have to have an angle involved, okay? Depends on what kind of space you're in, what kind of angle. Okay, so a vector in a plane, such as your XY plane here or any kind of plane. So yeah, the definition is a directed line segment. So it is fixed on both ends. Okay. What I was describing before is what they call a ray. That's fixed on one end, it goes up. A vector, though, is fixed on both ends. Directed line segment. Geometrically, a vector in the plane represented by a directed line segment with its initial point, and this is let's use our graphic thing here. Okay? With its initial point at the origin, usually a good idea to do that. And then its terminal point somewhere else. Okay? And they say x1, x2, and I found that to be a bizarre representation of it. It seems like that should be x1, y1, because they named this the x-axis and named this the y-axis. So I'm going to call that x1, y1. Okay? Now I can't for the life, yeah, I know what we're going to do now. This is not the best way to do this. They should not name this vector x. Let's name this vector v. Okay? Then this will be v1 and this will be v2. Okay? That makes more sense. It doesn't make any sense to name this vector x and that coordinate x. It's too easy to confuse what you're talking about there. So let's name this v. And that's your x component, that's the y component. Or leave off the components altogether. If you're going to call this vector x, then this will be x1, that'll be y1. I mean x2, x1 and x2. And then those will be values that make more sense. I don't know why he did that, and I'm sorry I hadn't even noticed he did that before. But this is called the terminal point. This is called the initial point. Okay? Where it starts is the initial point, where it ends is the terminal point. Okay? A directed line segment. Now, if you set it up this way, with the initial point at 0, 0, terminal point at v1, v2, x1, y1, whatever you want to call that terminal point there, then that terminal point you can change and make that the vector components. These are coordinates of a point. They are components of a vector. The horizontal component, vertical component. That would be components of a vector. Now, here's something else that I found a little bizarre. I've used this author for 2 different books, Pre-Calculus Algebra and Calculus. I've taught 2 courses in Pre-Calculus, the Pre-Calculus book, pre-calculus algebra and pre-calculus trig, 3 courses from the calculus book, Cal 1, Cal 2, and Cal 3. And in every section, in every page of that book, he refers to a vector with an angle bracket, a point with a parentheses. In this book, same author uses parentheses for both vectors and points. And I don't know why. It would make more sense to use the angle bracket. So every now and then I might sneak up and put an angle bracket in because I'm used to doing it. And by the way, other authors use the angle brackets too. The same author uses angle brackets in 2 books and parentheses in this book. So the trouble with that is when you're looking at it, you don't know whether he's talking about a point or a vector. But angle brackets, you know he's talking about a vector. Now, I want you to notice something else, and we're almost out of time. In the book, when he's referring to a vector, and this is the only redeeming quality of what he had there, when he named this as vector x, and this is x coordinate, this was a little letter, maybe italicized, something like this. This was bold. Guess what? I don't write bold. So when I'm writing a vector, I put a vector symbol, an arrow over it to indicate this is a vector. And if I wrote the v here, that's just a number. That's a number. Okay. So without an arrow, it's a number. With an arrow, in the book it would be bold. When I write it, it's going to be with an arrow. I'll try to do it on the text on your test as bold, so it'll look more like the book. Okay. Let me get one more statement in. If you had 2 vectors in the plane, vector u, and we'll call that u1, u2, and vector v, we'll call that v1 and v2. Now this is in a plane, only 2 dimensions, okay? These 2 vectors are equal, u equal v, if and only if u1 is equal to v1 and u2 is equal to v2. Both of their dimensions have to be identically the same. One can't be positive or negative of the other or anything else, identically the same. That's the only way that 2 vectors will be equal. Okay? We'll begin next time with example 1. Okay. Good deal. Sorry we didn't get any further. Ooh. Let me erase that. All right. Have a good weekend. If you haven't finished your papers, please do your papers. If you haven't finished one of your tests, get as much done as you can so we can wrap it up next week.
When do you want test 3?
Whenever you can get it into me. Next week, preferable, so you don't have both of them out on the last weekend you got. Okay, so if you can get it to me next week, that'll be fine. So it's, technically a week from today, which is next Thursday, which is week, But you can, if you want to get it to me Tuesday, you can. That's fine. All right, good deal. We'll see you next week. Have a good weekend.